Hi, I'm Krishnakant Singh from TU Darmstadt and I will be presenting our work Glass, Guided Latent Slot Diffusion for Object-Centric Learning. This is a joint work with Simone Schaub-Meyer and Stefan Roth. Object-centric learning aims to learn a dedicated representation for each object in a scene. This is unlike traditional deep learning approaches which learn a monolithic representation for the whole scene. Object-centric learning has multiple potential benefits. These methods improve interpretability, generalize better to out of distribution scenarios, and facilitate different downstream tasks. Slot attention, the leading OCL approach, uses an encoder decoder architecture with a slot attention bottleneck. In the slot attention architecture, slots compete for explaining parts of the input via a softmax based attention mechanism. It supports tasks like property prediction, conditional and compositional generation, and object discovery. However, it struggles to scale to real-world scene. Dinosaur, an extension to the original slot attention work, learns in the space of pre-trained self-supervised features instead of pixels. This helps it scale to real-world images. However, these models do not support conditional and compositional generation. Stable LSD showed that by utilizing a pre-trained diffusion decoder in addition to a pre-trained encoder allows for conditional generation in addition to object decomposition on real images. However, it still does not allow for compositional generation and the generated images are not of high fidelity. The core issue with unsupervised OCL methods is that binding to objects without any guidance on what an object is an ill-posed problem. Latents often bind to object paths or group of objects. We aim to remedy this issue by using minimal supervision. Our first key idea for glass is to learn in the space of generated images from a diffusion model. These models capture the distribution of real images really well. Learning in the space of generated images helps us to utilize the cross attention maps from the diffusion decoder to act as a guidance signal to guide the slots. We label this guidance as semantic guidance. However, using cross-attention maps as semantic signal biases the slots to bind to semantic classes instead of objects as seen in the images. As seen, all three baseball players are represented by a single slot. To remedy this, we rely on instance guidance. We achieve instance guidance by reconstructing the encoder features from the slots. The pre-trained encoder features are more instance focused and help counteract the semantic guidance, making the model more instance focused. The combination of using instance and semantic guidance allows the slots to bind to object instances instead of classes. As can be seen, all three baseball players are represented by different slots here. Glass learns a general purpose object centric representation which enables multiple downstream tasks such as object discovery, conditional generation, compositional generation, and property prediction. Our method outperforms previous methods on object discovery metrics like MIOU and MBO for COCO and BOC datasets by a wide margin. Glass produces cleaner boundaries compared to dinosaur and stable LSD. Moreover, our approach is more instance aware than spot. As seen, our method generates images which are of much higher fidelity than stable LSD. Glass is able to compose objects between different scenes. Here we see our approach is able to add a wide variety of objects to a new scene. Our method is also able to remove highlighted objects from the input while retaining the background and other objects in the scene. In summary, we find that training on images generated with diffusion models generalizes to real images, guidance maps help learn better slot representation for multiple downstream tasks, jointly training the diffusion decoder helps generate high fidelity images and enables compositional generation. To conclude, we present GLASS, which sets a new SOTA for object discovery among OCL methods. It outperforms existing methods in zero-shot generalization and enables compositional and conditional generation for real-world scenes. Thank you for listening. Please visit our project page for additional details and our official implementation.